going to start chapter 3. Chapter 3 basically, let me see. This is chapter 3. You see, chapter 3 talks about exponential functions and logarithmic functions, and as I advertised previously, chapter 1 just talked about functions in general, chapter 2 about polynomials. Now chapter 3 is about exponential and logarithmic functions, and that's what we're going to do here. Okay, so exponential functions are one of the most important functions in entire mathematics. Okay, and there are a lot of situations in real world that can be described by exponential functions. In fact, we're going to have two sections that kind of touches on those two topics, applications of exponential functions. But for right now, we're going to define exponential functions and look at some of its properties and just build on that definition and see how far we can go. Okay? We're going to start with the basic exponential functions. Of course, we have variations of it, but the basic one, the one we're going to discuss right here, is defined as the following. We start by a real number a, which is a positive number, okay, and not 1. The case a equal to 1 is not an interesting situation. So a has to be not negative or 0, bigger than 0, and not 1. So it could be between 0 and 1 or bigger than 1. And of course x represents your variable, and then the function f of x defined by a to power x. So is a that we chose, this real number, is the base, and your variable x is the exponent. Okay, so f of x equal to a to power x. This is called an exponential function. Okay, here are some examples. Remember, base doesn't have any x in it, variable. Your variables are in the exponent. Okay, and this a cannot be negative or 0. 1, it could be 1, but case a equal to 1 really is not an interesting case. It's a constant function. Here are some examples. F of x equal to 3 to power x. In this case, your a is 3. This is not an exponential function, okay? Because your base has x in it, and exponent doesn't have any x. This one is a is 2.75. So check mark means these are exponential functions. Star means they are not exponential functions. This one is not. You see, this one not only has x in one hand, has x in exponent like this one does, but at the same time it has the x in its base. So this is really not an exponential function either. This one is, your a is 4/7. This one is not. This is actually a rational function. Okay, this is a power function. Well, it's between power function and exponential. But I don't want to put a name on it, so it's not exponential, whatever it is. Okay. If a is not equal to 1 and b is bigger than 0, then what if I put a negative for exponent right here? This is also an exponential function that can be written in terms of this exponential function. Okay, all you have to do is to use the idea that you learned in previous class, that m to power -1 actually 1 over m. You see, we learned that. So if I use this idea from an intermediate algebra course, previous course that you took probably, so if I have b to the negative x, then I can change this negative to positive x as long as write this b as 1 over b. And then this becomes like this function, a to power x, but your a is 1 over b. See? So whether you have negative exponent or positive exponent, you can always write them as positive exponent, okay, by converting the base. Like here, f of x equal to 3 to power negative x is actually 1/3 to power x. Okay, so this is an exponential function. So your a is actually 1/3. If you want to compare it with this guy, your b is 3. You see, this one. You have a 2/3 to power negative x. You can replace that negative by positive x as long as you reciprocate your fraction. So instead of 2/3, you write 3 over 2. 2 over 3 here, 3 over 2, then you change this negative to positive. Okay? So actually, maybe I should have said something here actually. So if I say, let me just write it in this box. Okay, if I say f of x equal to m over n to power x negative x, this is the same thing as n over m to positive x. Maybe I should have said that. You see, if you have m over n to power negative x, then change negative to positive by writing n over m instead of m over n. Okay? But I'm using this idea here, you see. So f of x equal to 2/3 to negative x is the same thing as 3 over 2 to positive x. And here, you see, I can use this idea. 0.25 to power negative x is 1 over 0.25 to x, and if you divide 1 by 2.5, you get 4. If you use your calculator, if you don't believe me, you can always see if I can get away with this one here. You see, 1 divided by 0.25. Now, let's look at more involved forms of exponential function or variations of exponential function where you actually have something more than x in your exponent. You see, so in general, I have something like, let's say, f of x equal to a to power u of x. You see, that means instead of just x, you have something more than x. So if u of x is x, you get that. You see, so if u of x is x, right here, then you get that. But u of x doesn't have to be x; it could be something more than x. Okay, so these are also considered as exponential functions. They are more involved. Okay, because not always you have just a to power x. You may have something more than x up there. Like here, f of x equal to 3 to power 2x plus 1, or g of x equal to 2 to power x squared minus 5, or h of x 2 to power x minus 3 over 2x plus 1. So in this case, this is your u of x. This is your u of x, and this whole thing is u of x. See, Like, if you want to find f of 1, you simply replace x by 1. So this is going to be 3 to power 2 times 1 plus 1. So 3 to power 2 times 1 is 2 plus 1 is 3. 3 to power 3 is 27. G of 3. G of 3 means in G right here replaces x by 3. So you get 2 to power 3 for x squared minus 5. This is 2. 3 squared is 9 minus 5. And 9 minus 5 is 4. And 2 to power 4 is 16. Of course, x doesn't have to be like a 1 or 3 or something nice. Could be decimal. Okay, I'll show you one example. Just a second. Of course, you can always use your calculator to find these exponential values. H of 1. H of 1 means replace x by 1. So this is going to be 2 to power. We use green here. So you go. X is 1. So it's 1 minus 3. 1 for x. And then 2 times 1 plus 1. If I work this out, I get 2 to power 1 minus 3 is negative 2. 2 times 1 is 2 and 1 is 3. So 2 to power negative 2/3. Then of course this is not like 2 to power 4. I can do it without a calculator, or 3 to power 3. I can do it without a calculator. But here actually I have to use a calculator. So here's your calculator. If I zoom this up, you see like this, I have to do 2 to power negative 2/3. So here we go. 2 to power parentheses negative 2 divided by 3. So here I get approximation. You get about 0.629. So I want to round it up to 0.63. Let's go back here. Let me say this is approximately 0.63. Okay. And if you want to do f of negative 2, this is your f. F of negative 2 is equal to 3 to power 2 times negative 2 plus 1. So this is 3. 2 times negative 2 is negative 4, and 1 negative 3. Now if you want to do this just directly with your calculator, you can write this one as so say 3 to power negative 3, like that. So you get that, and let's see if we can make it like a fraction. So say math 1. So this is actually 1 over 27. This is equal to 1 over 27. The previous one, I don't know, maybe wouldn't work out that way. Okay, now let's make this one bigger a little bit. Okay, now let's look at the graphs of exponential functions. How does the graph of exponential functions look like? Okay, in order to answer that question, what we're going to do is to actually, without a graphing calculator actually by pointwise technique that we discussed before, sketch the graph of two very basic exponential functions, and then use those two to kind of get a general idea how all exponential functions look like, and as well as the graph is concerned. Okay, so those two functions are actually the simplest ones that we can choose: 2 to power x and 2 to power negative x. Okay, so we're gonna actually sketch the graph of these two functions manually, you know, and then we check them out with a graphing calculator, and then after that, after we get this general idea, then we can use a graphing calculator for future graphing of exponential functions. So how am I going to do? Of course, I'm going to use my calculator if necessary to compute numbers, not graphing. Okay. But when I say not using graphing calculator, I mean not graphing the actual graph. Okay. So this is, I want to compute values for certain x values for both of these two functions and graph both of them on this xy plane, and kind of, you know, get some idea how they are related actually. Okay, so let's start with 0. If I put f of 0, you see f of 0 is 2 to power 0, and 2 to power 0 is 1. So g of 0 is 2 to power negative 0, which is again 2 to power 0 is 1. So both of them are 1 and 0. Okay. Let's try 1. F of 1. F of 1 is 2 to power 1, and 2 to power 1 we all know is 2. G of 1. G of 1 is 2 to power negative 1. 2 to power negative 1, again, if I use this idea we just discussed it, if I use this idea, m to negative 1 is 1 over m. This is simply 1 over 2, 1/2. Let's try 2. F of 2. F of 2 is 2 to power 2, and 2 to power 2 we all know is 4. And then if you do it for g, g of 2 is 2 to the negative 2, and this is actually 1/2 to 2, which is 1/4. It's smaller so I can see both sides. I think you can't. Let me do it. Okay, that's better. Let's try 3. F of 3 is 2 to the 3rd power, which is 8. G of 3 is 2 to the negative 3, and then this is nothing but 1 over 8. 8 and 1 over 8. And now you can use negative values. F of negative 1 is 2 to power negative 1 is 1/2. So this is 1/2. And g of negative 1 is 2 to the negative times negative 1 is 2 to the 1 is 2. So you get 2. Now I get backward, you see. When I go positive values 1, 2, 3, f is 1, 2, 4, 8, and g is 1, 1/2, 1/4, 1/8. But if I go to negative, then I get 1/2 here, 2 there, just like you see this swap. Like f of negative 2 is 2 to the negative 2, which is 1/4. This is going to be 4. G of negative 2 is 2 to the negative times negative 2 is 2 to the 2 is 4. See? And finally 3. F of negative 3 is 2 to the negative 3, and 2 to the negative 3 is 1 over 8. g of negative 3 is 2 to the negative times negative 3, which is 2 to the 3, which is 8. Like that. So this is my table. I can do this forever, but we don't have time to do this forever. Now let's plot points. Let me use green for f. So I'm going to start with 0, as 0 is 1. You see? 1, 2, 3, 4, 5. Yeah, actually, yeah, I think I can use that. At 0, you have 1. This is 0, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and so forth. And here's 1, 2, 3. So at 1, at 0 is 1, and then at 1 is 2. So at 1 is 2. See? At 2 is 4. At 2 is 4. 1, 2, 3, 4. At 3 is 8. 1, 2, 3, 4, 5, 6, 7, 8. And that's it. Okay. Now if I go to the negative value, at negative 1 is 1 half. At negative 1 is half of this 1. This height is 1. Half of it is 1 half. You see, like that. Then at negative 2 is half of this half. So this is half of it's already. Half of that is going to be a little smaller, will be very closer to x-axis, you see, like this. And then at negative 3 is half of that, which is very close to x-axis, you see. So can you imagine, as you go to the left, this point is going to come down and down, but it's never 0. So that means they stay away from x-axis. So that means as you go down like that, as you go to the left, the graph looks like this. Let me just draw. You see, if I start going to the right, start going to this point, if I continue this, it's going to go like that. You see, and if I go to the left, you see, as you go to the left, you get closer to x-axis. But you always stay away from x-axis. You don't never touch x-axis. You see, like this. So that means x-axis is an asymptote. You see, remember asymptote? So I expect this graph, as I go to the left, just continue going down, but never touching x-axis. You see, so like this. And as I go to the right, continues just like this to go up forever. And that is the graph of 2 to power x. See? Now if I do the other one with the red, see, at 0 you are 1, start right here. At 1 is 1 half. At 1 is 1 half. It's going backward. You see, it goes 1 half here. At 2 is half of that, 1/4, so it's a little bit half of that lower. And at 3 is 1/8, half of that 1/4, which is right here, you see. So it seems like now let's go to the left, what happens. If I go to the left, at negative 1 is 2. At negative 1, you are 2, you see, like that. At negative 2, you are 4. Negative 2, you are 4. See, this is 4, right? This is 5, this is 4. At negative 3, you are 8. Right here. So it seems like, now if I graph g of x, as I go to the right, the graph is going to go through this point, and it goes start going down, and as I go to the right to the positive infinity, this graph is going to get closer to x-axis but never touches x-axis, you see. So it's going to look like this. As I go to the right, left, goes like that. See, so I expect this to just continue going up, just like the other one. Okay. So these are the graph of 2 to the negative x, and as you can see, they are symmetric, mirror image. You see. Kind of interesting. So this is the general shape of these functions, you see. Just like, you know, all dogs actually look similar, all horses are actually the same, but they differ a little bit by color. And let me clean this up a little bit here. You do this a little bit. So you see, so as I said, you know, like, you know, if you look at all human, okay, all human, we all look alike, but they're quite different in terms of the height, and weight, hair color, eye color, and skin color. We are different a little bit. So the same thing, we have basic shape is the same, but they are different a little bit in many ways. These functions are also the same. The basic shape of the graph is the same, but the shape changes a little bit according to what the base is. Like for 2, or if I replace this 2 by 3, then it's going to change a little bit. And if I replace this x by something other than x, like by x plus 1 maybe, then same shape but is moved around a little bit. So as I said, the basic structure is the same. Okay. So now let's just look at these two for a second and answer a couple of questions, and then I want to use the graphing calculator. Let me actually graph this with your graphing calculator to see if we get the same thing. So let me make this one bigger a little bit. I go to y equal to, say, 2 to power x, see, and then I go to the second one, say 2 to power negative x. Okay. The window, I want to use the same window I had here from -5, so I'll go to window from -5 to 5, and from negative. So as you can see, these graphs here, for a second, just a second, they don't go below x-axis. So they're always positive, you see. So I really don't need negative x values. That means the range, this is what is discussed here. You see, domain and range, we're going to discuss it. So when I use my calculator, I really don't need very much negative y value. So I go from maybe -3 to, let's say, 10 for now. Okay, then I say graph. See, this is 2 to power x, and then this is 2 to power negative x. You see, as you go to the right, the graph kind of like an airplane landing, just kind of goes down, and then this airplane lands at infinity. It touches down at infinity. Or if this airplane touches down at negative infinity. See, if you want to kind of make that analogy, makes you understand it better. Now again, as I said, if you look at these graphs, let me make it smaller a little bit. If you look at this graph, what is the domain? Domain, you see, I can use any x value I want. In other words, this graph, as you can see, is continuous forever going to the right, and also continues going to ever to go to the left. So that means the domain of these two functions are from -infinity to infinity is the domain. And the range, as you can see, you never go below x-axis. That means y values will not be negative, and you also won't touch x-axis. That means 0 is not part of the range either. So the range is 0 to infinity. So you see, this is the range, and then this is the domain. The same thing. Domain is minus infinity to infinity, and range is 0 to infinity. And horizontal asymptote. This is horizontal asymptote. This curve, as you go to infinity, becomes flat, just like x-axis. So horizontal asymptote for f is x-axis. X-axis is actually the horizontal asymptote. The same thing for this one, x-axis. Okay. Now I have two examples here. You can do it the same way, but what I'm gonna do, I'm gonna do these two functions on my graphing calculator along with what I already have. See? So I'm gonna go to y equal to, you see, I have 2 to power x, 2 to power negative x, then I'm gonna go to 3 to power x, and then I'm gonna do 3 to power negative x. Okay. See what happens. So actually, I'm gonna let's say 2. I want to do all of them again together. Okay. So if I say hit, see, this is 2 to power x. This is 2 to power negative x. This is 3 to power x. This is 3 to power negative x. And as you can see, as the base 2 becomes 3, this is 2 to power x, the next one is 3 to power x. So it seems like on the right side, 3 to power x goes to infinity much faster. This is a little bit flatter, you see. And as you go to the left, it goes to 0, or goes closer to x-axis much faster. So, in other words, if I want to do this on my graphing calculator, let's see if I find another color, blue. Here we go. Just use this blue here. You see, so it's going to be like this is 3 to power x on the right side is above 2.6, and on the left side goes below it, you see. Like that. And the same thing here, if you want to do 3 to negative x, on the left side to negative x is above 2 to the negative x, and the right side is below it. See, really it's too close. So if we want to actually see this phenomenon, maybe I should change my window. So I go from minus 2 to 2, and then here I go from maybe minus 0.1 to 1.2. See, this 2 to power x, this is 2 to power negative x. And let me just change my y value a little bit. Say 2. This is 2 to power x. This is 2 to power negative x, and this is 2 to power 3 to power x. This is 3 to power negative x. You see, 3 to x is above 2 to the x on the right side and below on the left, and 3 to negative x is above and on the right side is below. Okay, so kind of interesting. next thing we're going to discuss here is a special type of exponential function called the natural exponential function. This natural exponential function actually uses a very, very important number, as important as this pi is. You remember pi? We used it to find the area of a circle and perimeter of a circle, and its value is about 3.14, and this the decimals never repeat, nor do they terminate. So this is kind of rational number, irrational number. But as ugly as this number is, we use it to find the area of a circle. For example, if I have a circle like here, you see, if the radius is 3 feet, you want to find what the area is. Then you say area is pi times the radius squared, and if I put it in my calculator, I get this pi is built in your calculator because it's very, very important number. So actually, if you want to know how much it is, see it's right here, pi. See, pi. So I say second pi, about 3.14, 15, 92, 65, 4, and that's what I have here. And if you want more decimals, you have to use a bigger computer. Okay. And it's weird because you have to use it. You don't even know the exact value, but you use it to find the area of a circle and the circumference. These are only two examples that you use it. You can use. They are being used. This number pi is being used in many, many different situations in mathematics. So we cannot avoid it. It just comes there because of the nature. This is what God did. Okay, kind of weird. There is another number called E. It's also similar properties. The irrational numbers, you don't know the exact value, and it's built in your calculator. And if you want more decimal, you have to use a bigger computer. Okay, and it's definitely is bigger than 1, and is a candidate for base of the exponential function a to power x. You see, so if I replace this a by e, I get a new exponential function called e to power s, called the natural exponential function. And this is the most important function in the entire mathematics. Okay, and it comes into play in many situations. Has all kinds of good properties, and so you can spend the whole. You can get a degree just studying e to power x. Okay. Using e to power x, presentation of many formulas become very simple and nice, and many problems in mathematics and real world can be modeled with this natural exponential function. In this exercise, you've been asked to actually pointwise graph e to x, e to power minus x, just like we did 2 to power x and 2 to power negative x. Just fill out this table and plot points and connect to see how the shape looks like. Like, if you want to find f of 2 is e to power 2 and e to power 2. You can say second e to power 2 is about 7.4. You see, 7.39. If you want f of 3 is e to power 3, and e to power 3 is about 20.08 or 20.1. Okay. But this way you can complete this table and do points and connect. I'll let you do that as an exercise, okay? But but if you want to just do it on your graphing calculator to see how the shape look like, you can do it just like we did it for other functions. So see, second e to to power x, and then go down here, say secant e to power minus x, and then the window, so let's say graph. It's typical shape of exponential function. I check, move my window a little bit. The shape is typical. The one under this one is e to the power x, this one is e to power minus x. Okay? So typical shape of a exponential function. To continue this to this following example, we're going to graph other exponential functions which are a little bit more involved than just simple exponential functions. E to power x and e to minus x or 2 to x or whatever. They're a little bit more involved, like these. You see, minus e to 2x minus 1 plus 2. See, this minus kind of reflects. This minus 1 kind of move it to the left and right. This plus 2 kind of moves it up. Okay? And this one, you see, this x squared makes it look like a parabola, and this one makes minus 4 moves it down. So actually, I use my graphing calculator to get them like this. So let me just show you how this works. See? So clear. So I'm going to type this one, minus secant e to power 2x minus 1 plus 2. See, I'm doing this function right here. So I'm going to change my window to minus 8 here. This is the window I'm using. Minus 5 to 5, minus 8 to 5. So it looks like this, you see. Seems like as I go to the left, it kind of levels off at certain height. That would be your horizontal asymptote, and then I go to the right, it just falls down and goes to negative infinity for y value and positive infinity for x value. Okay. So if you see at what point levels off, you can use a horizontal line. So I say second draw, then use number 3 horizontal line, and then look at your y value. You see, about 2.08, about 0.2. See, and level off at 2. So what I did here, then I drew a horizontal line at 2. That's your horizontal asymptote, and kind of mimic my graph. Similar. You can do the same thing with here with this function. So if I go ahead and type that one in, this one is 3 to power x to power 2 plus 1 minus 4. As I said, this x squared would make it look like a parabola, and this minus 4 kind of moves it down 4 units. So if I say graph, see, so it seems like, it goes to negative 1 below here, down here, and then 0.5 to the right, negative 0.5 to the left, and kind of, I don't want to spend too much time on this, but this is 1 here, this is negative 1 there, so 0.5 here, 0.5 there, and this is negative 2, this is negative 1, so kind of U-shape goes down. Okay, that's the graph of these functions. Now, what we're going to do, we're going to look at some general properties of these exponential functions. Okay, general properties. So to do that, we actually look at the graphs. So I want to use these graphs as typical. See, these graphs that we did here. This is 2 to the x, 3 to the x, 2 to the negative x, 3 to the negative x. So I'm going to discuss the properties of graph of a to power x in general. Certain properties that they all have, no matter what a is, they share all these properties. Okay. The first thing is that the domain of these functions a to power x is the whole real line, minus infinity to infinity, and the range is 0 to infinity. You see, you can see it here actually. We did it for these two functions, but in general, it doesn't matter. This is 2 to the x or 3 to the x. I can use 4, 5, 6, 7, whatever numbers. It's still the same thing. Domain is minus infinity to infinity, range 0 to infinity. You see, because you don't go below x-axis, so there is negative y values are not attained. Okay, and you can use any x values. So the domain is for real line, and range is just half line. 0 is not included. The y-intercept is 0, 1. You see, all of them, they go from the same point here. You see, this is the y-intercept, which is 1. 0, 1. So 0, 1 is the y-intercept. They all go to the same one. Okay, same. So it doesn't matter how many I do. Let me see if I can do a couple more here. Like if I do 2 to the x, 3 to the x, 1.5 to the x, 4 to the x. You see, they all have the same y-intercept. You see, it doesn't matter. This is a 1.5 to x, this is 2 to the x, this is 3 to the x, this is 4 to the x. It doesn't matter. They all go through the same y-intercept. Okay, so the y-intercept is 0, 1 for all of them. No matter what a is, the y-intercept. X-axis or y equal to 0 is the horizontal asymptote. You see, just like an airplane landing to the left and right, as you go to the negative infinity or positive infinity, you level off with x-axis. So x-axis is the horizontal asymptote. Okay. The function is increasing for a bigger than 1 and decreasing for a less than 1. You see, actually here, if I have 2 to the negative x, you see, 2 to the negative x is actually 1/2 to power positive x. So this 1/2 is less than 1. So seems like, so this one is, this right here is 1/2 to power x as well. So as you can see, when your base is less than 1, you get decreasing. This is 1/3 to power positive x. This is 3 to, so when your base is bigger than 1, you see it's increasing, going up. When bases are less than 1, like 1/3 or 1/2, the graphs are decreasing. That's what we have. So the function is increasing for a bigger than 1 and decreasing for a between 0 and 1, for less than 1. It cannot be negative. You see? So in fact, just let me just show you one here. See, I'm going to make it bigger here. Let me say 3 to power x, graph it. This is increasing. Let me change my window. This is increasing. Now if I go back here and then do another one, let's say 0.75 to power x. 0.75 is less than 1. You see, this is 3/4, actually 3/4. Then if I say graph, you see, it's decreasing. So for a bigger than, so here you have it. For a bigger than 0, bigger than 1 is increasing. For a less than 1, of course bigger than 0 is decreasing. And they are one-to-one. You see, if you draw horizontal line, they pass horizontal line. Yes. So they are one-to-one. And this one-to-one implies that if I have a to power r equal to a to power s, in other words, if the bases are equal, then the exponents must be equal. You see, this is a very important property here, this one. Make it bigger actually. You see, so this one says if I have one exponential equal to another exponential with the same base, a to r, a to s, then these two r and s must be equal. That is because the functions, exponential functions, are one-to-one. That's why. Okay. Actually, among these properties that I've discussed here, this particular one is the one I'm going to show you in the next example, how to use this particular property to solve so-called exponential equation. Okay. Exponential equation, we're going to discuss that. Exponential equations are those equations whose unknowns are in the exponent. Okay. So right now we're going to discuss a particular form of these. There are more. These exponential equations are. We're going to discuss them in more general setting later on. More general form of exponential equations. But for right now, because we don't know very many techniques of solving all those equations, we just restrict ourselves to certain types of exponential equations. What certain type? For those exponential equations with the same base on both sides. You see, if I have a to power r and a to power s, I can use r equal to s to solve equations. Okay, so I can use this formula right here if and only if the bases are equal. If I don't have equal bases, I have to make the bases equal somehow, or use other techniques if I couldn't make the bases equal. For this example coming down here, are these examples are situations where either the bases are actually equal, and if they are not equal, then we can make them equal. Okay, so I'm going to show you what I mean by that. So here we go. Exponential equations, as I said, are those equations where your unknown x appears in the exponent, like here. You see, so here I have 5 to power 3x minus 7 on the left side equal to 5 to power x plus 5. I want to know what x is. How much is the value of x that makes the left side equal to the right side? Then you say, well, I have 5 as a base here, 5 as a base there, so this exponential on the left and this exponential on the right, they have the same bases. So I can use this property right here. You see, since the bases are equal, I can put exponents equal. So I can say this implies that 3x minus 7 equal to x plus 5. You see, I can put this exponent equal to this exponent. Now this is a linear equation that we've solved before, so I add 7 to both sides and subtract 5. So add 7 to both sides and subtract 5 from both sides, like that. So maybe I shouldn't do that. Let me erase this and do it over again. As I said before, you can always move anything from one side to the other side, change the sign. So I'm going to put x's together. So this x goes to the left side, this 7 goes to the right side, you change the signs. So I get 3x minus x equal to 5 plus 7. You see, this negative 7 goes to the right side, becomes positive 7. This x goes to the left side, becomes negative x. So 3x minus x is 2x, equal to 5 plus 7 is 12. So x is equal to 6. So I solved this equation. Okay. For this one, you see I have a 3 as the base here, and 27 doesn't even have is a base, but it's not 3. But 27 is 3 to power 3. That's what 27 is. 3 to power 3 is 27. Now I have one exponential on the left, one on the right with the same bases. So in this case, you see, first I didn't have the same base. You see, I have base 3 here and base 27 to power 1 there. But I made the bases the same because 27 to power 1 is the same thing as 3 to power 3. Now I can say, because the bases are equal, like here, you see, this is 3 to power x plus 5, this is 27 to power 1 actually. So we have different bases, but 27 is 3 to power 3. So I made the bases the same, just like I have here. So I can put the exponents equal. So that means x plus 5 is equal to 3. So if you subtract 5 from both sides, or move 5 to the right side, x is equal to 3 minus 5. So x is equal to negative 2. Okay. How about this one? Well, you have one exponential on the left, one exponential on the right, but they have different bases. But 8, you know 8 is 2 to power 3. You see? So I replace this 8 by 2 to power 3, I would get 2 to power 5x minus 1 is equal to 2 to the third power for 8 to power x plus 1. Okay, and you know from intermediate algebra, you see 2 to the power 3 is 8 for one thing. So I replace this 8 by 2 to power 3, and now you use this idea of a to power n, all of it to power m is a to power n times m. You see, you multiply these powers, then you come one after another. So if I use this idea, this is the same thing to say 2 to power 3 times x plus 1, like that. So if you compare the left side with the right side, you see you have the same bases. So you put the exponents equal. So 5x minus 1 equal to 3 times x plus 1. And now I can solve this equation. Distribute this 3, you get 3x plus 3. Okay. This 3x goes to the left side. This 1 goes to the right side. So I get 5x minus 3x is equal to 3 plus 1. 5x minus 3x is 2x equal to 4. So x is equal to 2. Now this one, next one, (81) is actually 3 to power 4. That's what 81 is. 3 to power 4. So Now I have one exponential on the left, one on the right, both have the same basis, so exponents must be equal. So 2x plus 5 is equal to 4. I can move this 5 to the right side, so I get 2x is equal to 4 minus 5, 2x equal to minus 1, so x is equal to minus 1 half for that situation. Two more. This one is already have this. These two already have the same basis. So x squared minus 2 equal to 3x minus 4. Now this is a quadratic equation. See, when I did these problems, x didn't have power to. They are linear equations. But here, because it's quadratic, I have to use quadratic formula or factorization. But I have to put everything on one side. So move everything to the left side and change the signs. Like say x squared minus 2 minus 3x plus 4 equal to 0. Simplify one more time. X squared minus 3x plus 2 equal to 0. I can factor this. X minus 1, x minus 2 equal to 0. If I put this one equal to 0, it gives me x equal to 1. If I put this one equal to 0, it would give me x equal to 2. And these are the solutions. If you couldn't factor, then you could use quadratic formula. I'm not going to do this one for now, so forget about it. Okay. Well, now let's look at some applications of exponential functions. One application is when you use exponential function for interest. When you save money, when you invest money, you get interest on it. So the first part really doesn't involve exponential, but when we get to compound interest, then we're going to see the application of exponential. Okay, so the idea is when you save money, invest money in a bank, or borrow money for whatever reason, then you get interest if you invest, and you pay interest when you borrow money. Okay, and that's how capitalism works. So that's why they say the rich gets richer, because the rich has a lot of money. So let people borrow their money. When they get it back, they get some extra back. So they make money out of their money. And the poor gets poorer. Poor doesn't have money. They borrow money. After they pay it back, they pay a little bit more. So this is terrible, but that's how it is. That's how capitalism works. Okay, so anyway. So there are basically several kinds of interest you can accumulate on a money, either borrowing or investing money. We're going to look at 3 different kinds of it in this application, in this course. Okay, so we have simple interest, we have compound interest, and we have continuous compound. Okay, simple interest, as the name suggests, is very simple. Okay, so that's the one we're gonna consider, and this simple interest actually does not involve exponential functions. Okay, but compound interest and continuous compounding do. So let's discuss simple interest, and then we get to the other type of interest later on. Okay, so simple interest is like this. In this method, interest is calculated solely as a percentage of the principal sum. Principal sum is the amount of money that you start with. For example, if you invest money, you put certain amount in the beginning. That's the principle. Okay, we call it P. We deposit P dollars, or we borrow P dollars. That's the principle. Okay, and then simple interest is calculated as a percentage of this principal for each year. Okay, so you say, for example, so many percent of this every year is the interest. Okay, so here's how the problem goes. Suppose you invest or deposit P dollars in some account, and that account gives interest at the annual rate of R percent. For example, 6% every year annually. Okay, the amount of interest and the balance A is the balance after T years. So you put P dollars in an account that pays R% every year for T years. Then at the end of the Tth year, A is the money that you have, your balance. How much money do you have? That's definitely more, because it's accumulating money, I mean interest. So if you are borrowing, then you borrow some amount of P dollars at R% for 10 years, and after that, then you have to pay it back. A is when you pay back, like a student loan. Okay, when you borrow money to go to school, then after you graduate and get a job, you pay it back, but you pay a little bit more because you have to pay interest. So as we said, interest is calculated for every year as a percentage of the principal. So interest is going to be rate R times the principal for each year, but you have T years, so you multiply it by T. So if you want to compute amount of interest after T years, multiply P by R and T. Of course, you have to use R as decimal, not percentage. And then if you want to know what your balance is, you add whatever amount of interest you got to whatever you started with. So you started with P dollars, now you made I dollars, so the new balance is P plus I. But P is P and I is PRT, so we can add those two. So if you want to know your balance, you can compute I first and then add it to P, or you can just put it in this formula. Or if you factor P, you get, I have too many equal sign here. If I factor this P, so A gonna be P times 1 plus R. So if you want to compute your balance, you can use this formula. If you want to compute your interest, you can use this. So, for example, if you invest or deposit $1,200, so P is $1,200, sorry, and the annual rate is 2.5%, so R is 2.5%. In decimal gonna be 0.025, so you use 0.025 in calculations, and then you wanna leave it in there for 6 years, so T equal to 6 years. So you wanna know how much is your balance after 6 years. So you say, so it says, let's see what, calculate the amount of money in the account at the end of the 6 years. So it's simple interest. So I can do it like this. The interest is PRT. P is 12,000. R is 0.025, and T is 6 years. So if I use your calculator, multiply these, let's see what do we get. We get, let's see, we get 12,000 times 0.025 times 6. So I have 1,800. So That's your interest. After 6 years, your money is increased by $1,800. So A is whatever you had, which was 12,000 plus whatever you made, 1,800. So it's going to be, let me, if I add this to 12,000 plus 12,000 is $13,800. Okay. So your simple interest after 6 years, you have $13,800. Okay. Now, what is compound interest? Compound interest is that this method, a year is divided into k shorter periods. For example, you do it every month, so you do it 12 times. You divide it to 12, or so they call it monthly. So if you do it compound monthly, that means you divide 1 year to 12 months. Or if you want to do it weekly, it's 52 weeks. You do it every week. Or if you want to do it daily, you do it every day. So you divide a year to k shorter period, whatever that k is. For example, if you do it monthly, k is 12. If you do it quarterly, k is 4. If you do it weekly, then k is 52. And if you do it daily, k is 365. Of course, you can do it hourly, then minutely, secondly. So it really doesn't matter. K can be as big as you can. So that's the question we're going to answer. How big can k be? Okay, we discuss that later. But the most popular k are 12 for monthly, 4 for quarterly, 52 for weekly, and 365 for daily. Okay. Then interest is computed not only on the initial principal but also on the accumulated interest of each period. So what it means is this. Let me just draw something here. You see. Basically, what we're trying to say is this. Let's say this is 1 year, and I divided to k equal periods. So let's say, for the sake of discussion, to 4. We want to do it quarterly. Okay. So you start with p dollars in the beginning. Then you compute interest on the first period, I1. At the end of the first period, your new balance is P plus I1. Okay, so this is your new balance at the end of the first period. And then for the second period, now you compute interest for the second period. But you compute that interest for the second period based on this guy, which is bigger. You see, because it's bigger, then you get a bigger interest, I2, on the second period. So at the end of this period, how much money do I have? P plus I1. I had it here. Now I have to add I2 to it. You see, it's bigger, even bigger. Then for the third period, you compute interest, but based on this guy, which is bigger than this. Therefore, you get I3, which is bigger. I see I3 is bigger than I2, and I2 is bigger than I. So these are all bigger. You see, like that. Then finally, on the last period, you compute. So at the end of the third period, your balance is P plus I1 plus I2 plus I3. You see, it's bigger now. Bigger than that. So when you compute the interest on this period based on that, you get a new interest I4, which is bigger than the previous one. So this is just like an avalanche. You see, it's accumulating, compounding. Like, you know, this analogy you make, like an avalanche. You have a lot of snow here, and then a little bit of snow gets loose. It's P. And then as it moves, carries more snow, so when it gets here, it's even bigger now, you see. Now as it moves down, because there are a lot more snow in the way, it gets bigger. You see, it's compounding, you see. You see, just like that. That's what happens to your balance. After so many periods, your balance, just like this avalanche, getting bigger and bigger and bigger, and then finally when it gets to the lowest part, is really big. So at the end is really big. This is called compound interest, because you're compounding your interest on whatever you had on the last period. It is bigger. We can discuss and use this idea here to derive a formula for the balance, but we are not going to do that. Okay, we are not going to derive the formula. We just tell what the formula is, and we learn how to use it in problem solving. You see, again, here's the problem. In this method, as we described, in this method, a year is divided into k shorter period. Interest is accumulated, calculated not only on the initial principal, but also on accumulated interest of each period, just like here, you see. So, if you invest $P in an account that pays R% rate yearly, and you compounded K times a year. Here in this discussion, I said 4 times a quarter, maybe monthly is 12. Whatever K is. So you divided year to K. If you divide a year to K equal periods, then K times a year. So that means you divide 1 year to K equal periods. Then your balance at the end of the T years, after so many years you leave it there, after T years, is computed by this formula here. A, your final balance is your P, which is the principal times 1 plus R, the rate divided by K, which is that compounding number, to power KT. Now you see you have exponential. This is an application of exponential function, KT. So here, your future balance is given in terms of your initial investment. Now, sometimes you have the final balance, but you want an initial. So if I change, if I replace, if I want to, if P is the unknown and A is given here, P is the unknown. A is given. You use this formula. You want to know how much money, P, you have to invest in order to have certain amount A. For example, you say, okay, in 20 years I need to have $50,000. So that A is $50,000. How much should I put in this account to have that $50,000? So you are asking how much P is supposed to be. So if P is unknown, you use this formula. You see the difference is, here you have positive KT, here is negative KT. And here is A is by itself, here P is by itself. So if A is unknown, use this formula. If P is unknown, use this formula. Okay? So what we're going to do in the next example is that we're going to get the same amount that we computed here, $12,000 in that account with that rate 2.5% for 6 years. If I did it simple interest, my balance would be 13,800. But if you do it, let's do it compound interest to see if we do any better than 13,800. So we're gonna do compound interest for the same problem, but we're gonna do it 3 different ways: monthly, weekly, and daily. So for monthly, K K is 12. For weekly, K is 52. For daily, K is 365. Of course, this is the P, and this is R, okay, and this is T. So, and this is our formula. I wanna compute A for each one of them. So I say A is equal to P, right here, P, which is 12,000 times 1 plus R, 0.025 divided by K, which is 12, to power KT. K is 12 times T, which is 6. Okay, so I'm going to put this in my calculator. Let me show you how to put it in your calculator directly. That's the easiest way to do it. You see, I have it right there. I want to put this in my calculator. So I say 12,000, times parentheses 1 plus, do another parenthesis. In other words, what I'm doing here is to put another parenthesis right here. You see, this way calculator will read the whole thing correctly. So it's a parenthesis 0.025 divided by 12, close the inside parenthesis, close the outside parenthesis, to power 12 times 6. So if you say enter, your balance is going to be 13,939.80. So let me write it down. This is going to be equal to dollars 13,939.8. So as you can see, with the simple interest, our balance simple interest, the balance was 13,800, but when we compounded monthly, then your balance is 13,939.80. It's a little bit more, about $139.80 more. You see, so that's good. Even a penny more is good. Now we can even do better. If we do it weekly, it's gonna be even bigger. You see, so A is equal to 12,000 times 1 plus 0.025 divided by 52. So again, I'm going to put this in parentheses here, and then another parenthesis, to power 12 times, 52. 52 times 6. So let me see. 12,000. 1 plus parenthesis 0.025 divided by 52. Close the inside and outside parenthesis to power 52 times 6. So I get 13,941. So this is equal to $13,941.51. As you can see, it's even bigger than the previous. So if you do it weekly, you get about $2 more. You see, this is 39.80. This is 41.50. So about $2 more, which is good. Even a penny more is better than none. Now, if you do it for daily, A would be 12,000. 1 plus 0.025 divided by 365 to power 365 times 6. Again, put a couple parentheses there, and then put it in your calculator. 12,000, 1 plus parentheses 0.025 divided by 365 to power 365 times 6. So is a little bit more. For this you get $13,941.94. You see, if you compare it with the weekly, it's about 37 cents more. You see, 37 cents more, which is good. As I said, even a penny more is better than nothing. Okay. So as you can see, when you compound, not only you get more money, and then your money is going to be even bigger if you have a bigger K. Okay. Okay, the next example is the situation. The next example is the situation when you have your balance, but you want to know how much to invest. You see, this is the problem. It says, how much should be invested? So that means P is the unknown. How much should be invested in an account in order to have $10,000? So this is A. A is 10,000, so you want to have $10,000 in 5 years. So T, this is T. And of course, this is R. So P is the unknown. And as you remember, if T is the unknown, use this formula. P equal to A times 1 plus R over K to negative K. So we say P equal to A, which is 10,000, 1 plus R 0.03 divided by T. Interest is compounded quarterly. That means K is equal to 4 over 4 to power 4 times 5 years. Of course, negative of that. You see, negative 4 times 5 years. You see, there is a negative in the exponent. Okay, but that's the same thing. You just have to type it incorrectly. Say 10,000 times 1 plus another parenthesis here. You see, I put another parenthesis right here in order for this to be read correctly. Parenthesis 0.03 divided by 4. Close the inside and close the outside parentheses to power 4 times 5 years, 5. Of course, I forgot my negative. So negative 4 times 5. Say enter. So $8,611.89. So $8,611.89. Okay. So if you put this much in this account, this is what you have to start with P. Then after 5 years with this interest rate and quarterly compound, you will have that $10,000 that you want. Okay, so now the question is that I kind of raised that question. Let's go back to this page. K is the number of times you compound. So the point is, question is, how big of a K do you choose? Like in this problem here, this bottom problem, in one part K was 12, then 52, then 365. Let's say if you do it it's hourly. Hourly would be 365 times 24 would be 8,000. So if I do it hourly, then K would be 8,760. Kind of interesting. 8760. 876. Okay. Well, is this big enough? Well, maybe we could do it minutely. If I do it minutely, then I have to multiply this one by 60, because every hour has 60 minutes, so multiply this by 60. That's your K. You see how big it is? Now you can do it secondly. If I do it secondly, I multiply this by 60 again. Is this one? Okay, so can I do it smaller than secondly? Yes, you could, but the question is then, how big should K be? And if K is really, 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 really big, in other words, go to infinity, what happens to this formula when K goes to infinity? See, that's the question. If K goes to infinity, this formula changes shape. Okay, so if K goes to infinity, what happens is this. Show my picture if I can find my paper here. See, I have a I have A equal to P times 1 plus R over K to KT. Then in mathematical notation we say K goes to infinity. You see, when I say K goes to infinity, what does that mean? That means what happens to this formula when K is really big? 10 trillion. 5 billion trillion, you know, because there is no limit to it, it can go to infinity. So what happens to this formula when K eventually get to infinity, wherever that infinity is? So this formula is going to change shape. As time goes up, as K goes up, then this formula eventually changes. So as K goes to infinity, of course, in calculus and analysis, you can actually prove this, but with some process. But we are not going to do that here. We just write the result. When K goes to infinity, this formula changes to a new formula. It becomes A equal to P e to the RT. You see? So that is the new formula. K is infinity, so if I replace K by infinity, then this formula becomes this formula. And that's where this E comes to play. You see, that's exactly what happens. When K goes to infinity, something makes this whole thing to become E. So when K is really big, infinity, we call it continuous compounding. Continuous compounding. Continuous compounding means K has gotten really, really big and becomes this formula. So you read the problem and pay attention whether the problem says continuous compounding or non-continuous compounding, which is just regular compounding of certain number of times a year. Okay. So you usually, from the context of the problem, you know whether you have continuous compounding and not continuous compounding. And then you have to use appropriate formula for either case. Okay, so this is your formula. So if you see the word continuous compounding, that tells you use this formula. If they say compounding certain number of times a year, finite number, 10, 12, 20, 50, 100, then you use this formula. Okay, so you have to be careful. Whether it's a compounding, just regular compound certain number of times a year, or continuous compound. Okay? And that's your formula. You have to know it. Of course, if P is the unknown, you have the same thing with negative RT, depending upon what A. So let's just repeat example 7. What was example 7? Example 7 was this example that we did. See, example 6 actually. No, I'm sorry, I'm using the wrong paper. This one. Example 8 or 7. This the 7. So the simple interest. Now we're going to do a continuous compounding. You see, we did that simple interest. We got 13,800. Then we did the compound interest, regular compounding for quarterly or for monthly, got 13,939. Did it weekly, we got 13,941. And we did it daily, 13,941 and 94 cents. Now the question is this: what if I do it continuous compounding? And that's exactly what this problem is. So P is 12,000. R is 2.5%. And T is 6 years. Then continuous compounding is this: A equal to P e to the RT. So A is equal to P is 12,000. For P, and then E to power 0.025, multiply that by T, which is 6. So you put all of this in your calculator to see how much that is. That's the biggest thing you can get. This is ultimate. You cannot be any better than this. Okay. So let me see how much I get. 12,000. Maybe I should show it to you. See, I'm gonna put this in my calculator. 12,000. Then second E to power 0.025 times 6. I forgot. This is 6. Power 0.025 times 6. So you get 13,942. 13,942 cents and a penny, which is bigger than daily. Remember daily? That was daily. Daily was good actually. See, daily, your balance is $13,941.94. If you do it continuous compounding, it's $13,942.01. So it seems like about 7 cents more. 7 cents, you see? So it's more. By how much? Very little, but that's okay. Like if you are a banker, if you are like Bank of America and you have 20 million customers, and then they borrow money from you, and then you do it compound interest. Continuous compounding is better than daily because you get about 7 pennies, 7 cents more. So if you have 10 million customers, 7 pennies, 70 million. 70 million is about $700,000 that you make. So it works when it's big situation. But then if you just borrow some money from a bank, $1,500, and for like very short time and big interest rate, so you don't mess with it, just leave it simple interest. Okay, now he says how much will be invested. The same thing we had here, you see, the same problem, but he says use continuous compounding. How much money do I save, or how much money should I put in this account so I will have my $10,000? If I did it quarterly, I should put $8,611.89. But if I do it continuous compounding, see how much do I get? And this is the formula. But if P is the unknown, it's the same thing, but the negative RT. So P equal to A e to the negative RT. So P is equal to e to the negative R. R is 0.03 for 5 years. Okay, so let's see how much that is. If I put this in my calculator, this one's bigger. Say A. I forgot my A. I'm sorry. I thought there was something not right about this. Rewrite. So P is equal to A. A is 10,000. E to the minus R 0.03 times T, which is 5. I put this one in my calculator. And that's it. Look at this. 10,000 second e to power negative 0.03 times 5. $8,607. $607.08. So if you do it continuous compounding, you can get away with less money. You see, with less money to get $10,000 later. If you do it quarterly, you have to put a little bit more, $4 more. You see, so this thing saves you for $4. In order to get that $10,000, if you do it continuous compounding, you need to put $8,607.08. If you do it quarterly, you have to put $8,611.89 more. This graphical thing, I'm not gonna do it for now. Okay. When we get to logarithm later, we discuss that later. It's on here. This problem, I said, we don't. T is the unknown. T, something the exponent is the unknown. So I can do it graphically, but I come back to this problem later on. Okay. So that is it for section 3.1. So please review these notes and see this lecture one more time if you want to, and then attack your homework problems, homework assignment to see what you can. Okay, good luck. Let me know.